Welcome to G Fun Facts Online. Today, we are abandoning the usual warm intro to take you to the coldest place in the universe. We are diving deep into a story that combines quantum physics, a billion-dollar corporate gamble, and a scientific detective story that has shaken the foundations of modern research. This is the story of the Majorana Mirage. In the silent, frozen dark of a cryostat, temperatures sit a hair's breadth above absolute zero. This is where physicists have spent 20 years hunting a ghost. It is a particle that is its own antiparticle, a mathematical curiosity first conjured by the Italian genius Ettore Majorana in 1937, shortly before he boarded a ship to Naples and vanished from the face of the Earth. 80 years later, the particle that bears his name, the Majorana fermion, became the center of one of the most high-stakes, dramatic, and controversial sagas in modern science. It promised a revolution. If captured and tamed, these Majorana zero modes would not merely be another subatomic trophy, they would be the building blocks of the ultimate computer. They offered a path to the topological qubit, a quantum bit so robust, so immune to the noise and chaos of the outside world, that it would make the error-prone fragility of current quantum processors look like abacuses. By 2018, the world believed the ghost had been caught. A celebrated paper in Nature, backed by the immense resources of Microsoft and led by the luminaries of the field, announced the definitive signature of the Majorana. The champagne flowed, funding poured in, and the timeline for a fault-tolerant quantum computer was redrawn. But the ghost was a mirage. Today, in 2026, the landscape of topological quantum computing is a battlefield of retracted papers, ruined reputations, and a bitter, ongoing war between corporate breakthroughs and academic skepticism. We stand amidst a replication crisis that has shaken condensed matter physics to its core. This episode is the story of how the desperate desire for a holy grail blinded some of the world's smartest people to the messy reality of dirty materials, and how a billion-dollar bet on a beautiful theory collided with the hard, cold facts of experimental science. To understand the desperation, one must understand the stakes. The fundamental problem of quantum computing is decoherence. A standard qubit, whether it is a superconducting circuit like those used by Google or IBM, or a trapped ion, is an erratic entity. It must maintain a delicate superposition of 0 and 1, but the slightest whisper of heat, the faintest electromagnetic stray wave, causes it to collapse. To keep a quantum computer running, you need quantum error correction, a process that requires thousands of physical qubits just to create one logical qubit that works reliably. It is a brute force solution to a delicate problem. Enter the topological qubit. The theory, pioneered by visionaries like Alexei Kitaev and Michael Friedman, a Fields medalist who joined Microsoft, is elegant. Imagine a piece of string. If you twist it, that twist is a global property of the string. You can shake the string, stretch it, or dirty it, but the twist remains. The information is stored topologically, in the global shape, not the local details. In a topological quantum computer, information is encoded in pairs of Majorana zero modes, separated by a distance. Because the information is delocalized between two separated points, local noise, like a kick to one end of the wire, cannot destroy it. To process information, you do not pulse lasers or microwaves. You physically move these particles around each other, braiding their world lines like plaiting hair. The computation depends only on the topology of the braid, not the precise timing or strength of the operation. It is, in theory, inherently fault-tolerant. If you could build a topological qubit, you would not need thousands of backups for error correction. You could leapfrog the entire noisy intermediate-scale quantum era. It was the shortcut to the future. And for Microsoft, who had bet their entire quantum strategy on this distinct path, it was the only way to win the race against Google and IBM. The excitement began in earnest around 2010, when theorists realized you didn't need exotic, impossible-to-find materials to create Majoranas. You could engineer them. All you needed was a specific recipe. Take a semiconductor nanowire, like indium antimonide, with strong spin-orbit coupling, wrap it in a superconductor like aluminum, and apply a magnetic field. Under the right conditions, the electrons in the wire would pair up in a strange way, leaving half-electrons, the Majorana modes, isolated at the very tips of the wire. The signature of this state was predicted to be a zero-bias peak. If you tried to tunnel electrons into the wire, you would see a sharp spike in conductance exactly at zero voltage, quantized to a specific value known as 2e²/h. In 2012, a team at Delft University of Technology reported the first sighting. Their science paper, titled Signatures of Majorana Fermions, showed a zero-bias peak. It was cautious, but optimistic. The physics community was electrified. The Nobel Prize chatter began. Over the next 6 years, the evidence seemed to mount. Group after group reported similar peaks. Microsoft doubled down. hiring leaders like Leo Kuenhoven and Charles Marcus, setting up Station Q labs that blurred the line between university research and corporate R&D. The crescendo was reached in March 2018. Kuenhoven's group published a paper in Nature titled Quantized Majorana Conductance. Unlike the 2012 paper, this one didn't just show a peak, it showed a quantized peak. The conductance plateaued exactly at the theoretical prediction. It was the smoking gun. The uncertainty was gone. Microsoft's executives declared that a commercial quantum computer was 5 years away. But the unraveling was slow, then sudden. It began with whispers in the hallways of conferences. Two physicists, Sergei Frolov and Vincent Murik, both alumni of the Delft Group, started looking closely at the 2018 data. They noticed inconsistencies. The quantized plateau looked too perfect. When they requested the raw data, they hit a wall. But perseverance paid off. When they finally obtained the full dataset, the picture that emerged was damning. The 2018 paper had presented a clean, beautiful narrative. The raw data showed a messy, contradictory reality. Data points that didn't fit the theory had been excluded. Curves that showed the peak disappearing, which would disprove the Majorana hypothesis, were omitted. It wasn't just noise, it was selection. In March 2021, the 2018 Nature paper was retracted. The authors apologized for insufficient scientific rigor. An independent investigation by Delft University cleared the researchers of fraud, finding no evidence of malicious fabrication, but found them guilty of confirmation bias. They had wanted the Majorana so badly they had fooled themselves into seeing it. But the damage was not contained. The scrutiny spread. In 2022, a second Nature paper from the same group was retracted. A science paper from a different group claiming chiral Majorana modes was retracted after analyses showed the data was not just cherry-picked, but physically impossible, violating the laws of entropy. Another science paper received an expression of concern. By 2023, the field was in a full-blown crisis. The zero-bias peak, once the gold standard of evidence, was now viewed with deep suspicion. Why was it so hard to tell the truth? The answer lies in the Majorana mirage. The problem is that Mother Nature is a trickster. The recipe for a Majorana is also the perfect recipe for creating Andreev-bound states. An Andreev-bound state occurs when an electron gets trapped in a quantum, well formed by disorder or impurities in the nanowire. If the wire is a little bit dirty, and all nanowires are dirty, these trivial states can form near zero energy. Crucially, a trivial Andreev-bound state can look exactly like a Majorana zero mode in a tunneling experiment. It creates a zero-bias peak. Under certain conditions, it can even mimic the quantization. This is the bad actor problem. You are looking for a specific needle in a haystack, but the haystack is made of needles that look 99% identical to the one you want. The only way to distinguish them is through subtle, difficult tests, like checking non-locality or braiding statistics. For a decade, the community had been relying on a local measurement to prove a non-local property. It was like trying to prove a telephone line works by shouting into the receiver and listening for an echo, without ever checking if someone is on the other end. Following the retractions, Microsoft faced a choice: abandon the project or reinvent it. They chose the latter, but the strategy changed. The era of hero experiments by individual academic labs was over. The era of industrial quantum engineering began. Microsoft reorganized its efforts under the Azure Quantum banner. They stopped talking about discovery and started talking about protocols. In 2022 and 2023, Microsoft released a new criterion called the Topological Gap Protocol, or TGP. This was a rigorous checklist, a gauntlet that a device had to pass to be considered a topological phase. It required observing the transition into the topological state and observing the gap, the protection, simultaneously. In mid-2023, Microsoft announced that their devices had passed the protocol. They published a paper in Physical Review B, not Nature or Science this time, perhaps seeking a safer harbor. They claimed they had engineered out the disorder that caused the Mirage states. "We are no longer doing science," a Microsoft executive famously said in a press briefing. "We are doing engineering." But the community remained skeptical. The raw data for the TGP was complex, and critics argued that the protocol itself was circular. If you set the window of acceptance just right, you could still make a trivial state pass the test. This brings us to the present, early 2026. The Cold War between the skeptics and the believers has turned hot again. In February 2025, Microsoft made its boldest move since the 2018 retraction. They published a paper in Nature claiming a single-shot interferometric measurement of a topological qubit. This was the Majorana 1 chip. The claim was massive. They weren't just seeing a peak anymore. They claimed to have performed a parity measurement, distinguishing whether the electron number in the device was even or odd, which is the fundamental operation needed for a topological qubit. If true, it was the first step toward braiding. The backlash was immediate and ferocious. The stage for the showdown was the American Physical Society Global Physics Summit in Anaheim, March 2025. The session was standing room only. On one side was Chetan Nayak, the brilliant theoretical leader of Microsoft's quantum effort. He presented the data with the slick confidence of a tech product launch. He argued that the probability distributions and their interference measurements could only be explained by topological physics. On the other side was the resistance, led by Sergei Frolov, now seen by some as the conscience of the field and by others as its inquisitor, and Henry Legge, a theorist who had dedicated his work to debunking false positive signals. Legge took the podium and dismantled the analysis. He showed that the topological gap protocol used in the 2025 paper yielded different results depending on how you crop the graph. If you included the full voltage range, the topological gap collapsed. He argued that the signal looked indistinguishable from telegraph noise, random switching caused by trapped charges in the substrate, not Majoranas. Any company claiming to have a topological qubit in 2025 is essentially selling a fairy tale, Legge told the audience. Frolov was even blunter on social media, calling the Majorana 1 project essentially fraudulent in its presentation of data, though stopping short of accusing individuals of scientific misconduct. The 2025 Nature paper, unlike its 2018 predecessor, carried an editorial note of caution, but it passed peer review. However, the consensus at the conference was clear: not proven. Why does this keep happening? The Majorana saga is not just a failure of materials, it is a failure of sociology. First, the smoking gun fallacy. In condensed matter physics, we are used to indirect evidence, but the desire for a single unmistakable plot lead researchers to stop asking what else could this be, and start asking, does this look like what I want? Second, corporate science. The entry of big tech changed the incentives. When a research group becomes a division of a trillion-dollar company, the pressure to deliver milestones for shareholders conflicts with the slow, zigzagging path of basic research. A negative result in academia is a learning opportunity. In a corporation, it is a failed quarter. Third, the echo chamber. The field became insular. The same small group of people peer-reviewed each other's papers, hired each other's students, and validated each other's grants. When Frolov and Murik broke ranks, they were initially ostracized for washing dirty laundry in public. So, is the Majorana fermion a fiction? Most physicists still believe the theory is sound. The mathematics of topological superconductivity is robust. The problem is the materials. The indium antimonide aluminum nanowire platform, the workhorse of the last 15 years, may simply be too dirty. The interface between the semiconductor and the superconductor is plagued by atomic scale defects that may never be fully eliminated. There is hope in other directions, such as full-shell nanowires, a new geometry that might protect the system better, or planar Josephson junctions using 2D sheets instead of wires, or even completely different approaches like Kitaev spin liquids using magnetic insulators. As for Microsoft, they are pressing on. They have invested too much to turn back. They're building a massive new fabrication facility, betting that brute force engineering can eventually scrub the dirt out of the nanowires. They may eventually succeed, but the timeline is no longer 5 years, it is decades. The story of the Majorana fermion is a cautionary tale for the age of quantum hype. It reminds us that nature does not care about our stock prices, our grant applications, or our desire for elegant solutions. The Majorana mirage was not a malicious lie. It was a collective hallucination, born of the intense desire to see a beautiful theory manifest in the ugly real world. We saw the ghost because we wanted to believe in the afterlife of the qubit. Today, the field is wiser, sadder, and much more paranoid. The standards of proof have skyrocketed. A zero-bias peak is no longer a discovery. It is a starting point for an interrogation. The topological quantum computer may yet be built, but it will not be born from a single eureka moment in a press release. It will be built from the slow, grinding, unglamorous work of characterizing noise, eliminating defects, and accepting that in quantum mechanics, what you see is rarely what you get. The ghost is still out there somewhere in the cold, but we have learned the hard way. Never trust a ghost until you can braid it. Thanks for listening to G Fun Facts Online.